Okay, thank you. You're all the diehards, okay, so yeah, so let me remind you. Okay, so we have x and y. Okay, I'm not going to make the mistake of having z around anymore. It was too confusing. Okay, so these are, say, compact smooth manifolds, just so that I don't have to say words, maybe with boundary. Okay, and what we were doing was we were looking at the maps from x to y. Okay, and included in these maps, and it seemed like a good thing to do, was we were looking at the Lipschitz maps. Okay, and that because of compactness, the Lipschitz maps are dense inside of.
Can we just stick up?
Yeah.
I'm not sure we presume.
Oh.
So now you can.
Yeah. Now. Yeah.
Now you give the details.
Yeah. So now you're Stokes. Yeah. Yeah. No. And the Hodge conjecture. Yeah. Okay.
Okay, is it
Okay. Yeah. Okay. So we were right. So in order to, so it doesn't seem so terrible to replace the continuous maps by the Lipschitz maps. Right. They're dense, and that the inclusion is in fact a homotopy equivalence of spaces. So that seems like overall a good thing. And then we were looking at the Lipschitz constant. As being a map to R, or maybe log of the Lipschitz constant. Okay, and we did log just for a little, technical reason, because we talked about persistent homology and barcodes, and I won't repeat all of that, but I won't necessarily, I didn't actually define anything, so I just waved my hands and drew pictures, so I could do that again just faster. Okay. So we were interested in studying this in various settings, okay? And we did a little bit of anecdotal stuff, like when y was the circle or even non-positively curved, right? What started off by happening is, for L equals 0, you get, I'm going to put in a base point just to make everything starker. Okay, so that when I, map to the circle, I'll imagine that the base point goes to the number 1. Okay, just because, I'll tell you why. There's no great science here. I'd rather the topology when L equals 0 be a point rather than a circle. Right? We're talking about the constant maps. So, I'd rather there just be one constant. Okay? Right? So at time 0, I just get a point. Right? And for a while, this is in fact a convex set. Okay? So, that's what it looks like. Right? Then there's a moment when a new map exists. Okay? So the set of such maps, right, when y is the circle, the set of such maps are in a one-to-one correspondence with the first cohomology of x. Okay, so, right, so this is a lattice. Okay, so, so there will be a time when I begin picking up like a generator or two, and then what happens is, I begin having these convex sets, right? And then these begin growing, okay? Okay. So right. So we have a genuine picture of these spaces, okay? That was sort of just covering space theory together with a little bit of non-positively curved geometry, okay? And then there were various things that we studied. Like, so in the first lecture, we tacitly studied what were the volumes of these level sets. Okay, and we were saying that, the volume is growing like exponentially in L to the dimension of x. Okay, so that's, sort of, so how does the volume grow? So, these individual directions are, well, anyway, yeah,
So in the case that y is the circle,
yeah,
for some, as L rises, suddenly you get a map that's going to surgex onto the circle.
Right.
So you didn't have one before. So
You
it's
didn't-
not the new dot.
yeah, that's the new dot. Well, I mean, yeah, I mean, it happens to be the new dot. Of course, tautologously, the new dot was the first time that the map wasn't null homotopic. It happens to be that that's going to, the first time that you go over the circle is the first time that you, right? But it's not tautologously the case. So, some of these, at this level, a little bit beyond there, some of these will in fact be surjective as well. Okay? Okay? And the number of these, right? So the number of components is L, to the dimension of that first cohomology group. Okay, I guess that's the Betty number. Okay, right? So, so the non-positively, of course it becomes more complicated if this Y was a more interesting non-positively curved space. And of course, if I was going to talk about that, then I couldn't talk about anything else. Okay, but anyway, so this is a fair, and when we were talking about, so this was the picture that emerged, right? That had, that firstly, the number of, there's a very interesting phenomenon about here, that number of components is growing like a polynomial. That's not a non-positively curved phenomenon. Actually, usually when you have a little bit of negative curvature somewhere, the growth will be exponential. Okay? However, the exponential growth that you get, so now I'm just, telling you things, because I might as well, right? And it tends to grow like e to the L. So we saw that the volume of the individual levels is like exponential in L to the dimension of x. Okay? However, the number of components still is growing just exponentially. So there is, again, something beautiful, right? I mean, something should have been super exponential, and it's only exponential, right? I mean, you got to get into the mind that exponential is pretty small for some of these things, okay? But then on the other hand, right, I mean, they're sort of, that these things are fairly, fairly large, and we also know how to navigate these quite well, right? I mean, because these individual, each of these components is actually convex. That was sort of the nature of the analysis. Okay, there's sort of another extreme which we talked about, which was the case of a circle mapping to a space M, okay, where M has a complicated fundamental group. Okay, where by complicated we might say has unsolvable word problem. Okay, which is really an opposite extreme from this. Okay, and in that case, so by the way, so in terms of the homology, right, so we talked about the persistent homology and we talked about barcodes, right? So in this picture, right, there are no finite bars. Okay, right, so it seems like a lot of trouble to define a notion, and then there are no examples of it. But there is a little bit of information, which is where do the bars begin, right? Or how many bars are there, that are born before a certain time. And then that's a thing that, happens to be polynomial when you're going to the circle, but it's usually exponential, but it's not as super exponential as you might have imagined. Okay, and let's see, I did give some example where, I think X was the two-sphere and Y was the two-torus wedged with a two-sphere, where in fact you saw the super exponential growth of the number of components. Now, this one was interesting because, I drew the picture like this last time, right? So here you're having the constant loops, okay? And here you might have a complicated word, right, in the fundamental group, okay, which then corresponds to some path, that I just follow around the generators, okay? And when I discover, right, that when I discover that the word is null homotopic, that means that I found a homotopy. Okay, so if you think about it, I just want to write down the symbol, the inf over null homotopies. So let me call this thing W for word. Null homotopies, gamma sub t from G to the, to a constant loop, or the identity element of the fundamental group, however you want to think about it. The inf of the sup of the length of the curve, okay? Right? So this is sort of, a measure of how complicated the word problem is, okay? Because, you think, okay, this thing here is basically the length of the bar in pH0, whose bottom is the cycle W minus the trivial thing, right? So this is a zero cycle.
So W is G over here.
W is, yeah. Right, so I was having gamma sub t, and so W is a word, right? And, you see in this picture, so to speak, the difference between the words and the elements of the group. Right, I mean, okay, so this kind of thing, which is a kind of basic object in geometric group theory, is encoded in this persistent homology, okay? And the fact that word problems are unsolvable means that, well, if I knew a priori that there was some, bound like, 2 to the 2 to the 2 to the L, that I never have to go through curves of length like bigger than that, then, I would go up to that level. So, really, this function here tells me quantitatively, there's a quantitative connection between this natural geometric thing and the length of these persistent homology intervals. So one could reformulate, certain calculations in geometric group theory as being calculations of persistent homology groups, but typically of pH0 of the loop space. But of course one could study higher homology groups, and they are interesting, and they have some geometric applications, but there isn't much of, but I don't want to go in that direction. Okay, but one thing that we used this for last time was to prove, so to speak, in some sense we proved a theorem of Gromov that said if you have a manifold with this fundamental group, it always has infinitely many null homotopic geodesics. And the reason is you just look at one of these very, very long pH0 intervals, right? And at the bottom of it, right? I mean, what does it mean? It means that there's some component of some sub-level set, right? Which is, at the bottom of such a basin. And, so if I take that curve and then I, do some curve shortening process, it's going to end up at a geodesic. But on the other hand, since it's finite length interval, it means that it's representing the trivial thing. So, right, so that was sort of this very remarkable, if you think about it, it's sort of a very remarkable phenomenon, right? You have a hypothesis in logic, and the conclusion is that some differential equation, the equation of geodesics, it's a nonlinear second order differential equation, and it's saying that it has infinitely many periodic solutions, where the solutions have some property, okay?
So the null homotopy on the group theoretic level is just a sequence of relations that you...
Yeah, right. And, so you every time you have a relation, you interpret that as giving you an annulus. Okay, and then, you parameterize. Yeah, okay? So strictly speaking, if I really wanted to connect, this function here to the group theory, right, there's sort of two things. There's sort of a syntactic thing and a semantic thing, okay? Right, and you were doing the syntactic one, right? I mean, I told you if I have a group and it happens to be trivial, my solution to the word problem is always the same, namely, just say the damn element is trivial. Okay, you're asking, no, I mean, I should be able to do everything syntactically, and the algorithm I should use is I take the word and I apply every relation, and then try it again and again and again and again, you know, in this non-deterministic way, till finally I get to something where it was trivial, and I look at the smallest number of relations I use. So that syntactic thing is called the Dane function of the group. And if you combine this analysis with what I said about the entropy of the function space, you know, because this thing is going to be a path in the function space, it tells you that the logarithm of the Dane function gives you a bound for the persistent homology. So in fact, you can get an improvement of Gromov's theorem that if something's Dane function, which is a purely syntactic notion, is like 2 to the 2 to the L, right, then your thing is going to have infinitely many closed geodesics, and they're going to be able to beat competitors that are of size, you know, anything that's slightly sub-exponential in L. Okay, so you could make everything as quantitative as you want if you're, well, no. I mean, if you really want to be quantitative, then you never get as quantitative as you want. You know, for a non-quantitative person could say, you get as quantitative as you want by examining these relationships. Okay. So what, and I mentioned a theorem of the following sort last time, which I wanted to explore. So the theorem said, oh, okay. So let me just, I didn't say something. So one theorem that I mentioned is that if y is simply connected, then the number, I'll just talk about, you know, the number of homotopy classes represented by things of Lipschitz constant less than L, that this is O of L to some dimension. Okay? Just like the non-positively curved case. Okay? So this is somehow a reflection that homotopy theory, when you have a simply connected target, okay, is not logically complicated. Okay? But we want to understand sort of more geometrical things about this. Okay? And I'm just going to focus on H0 kinds of things about function spaces. Okay? Not the higher homology. I mean, I realize that's just too ambitious, you know, for this talk. So anyway, so we had some result of, well, like this. Another result we had was something along this side. If all the homotopy groups of Y are finite, then all the pH of maps from X to Y are infinite length or uniformly bounded length, where this bound just depends on the dimension of X. Okay? So this was the theorem that I mentioned last time that I didn't quite get around to proving. And I want to explore, you know, explore some of these phenomena. Okay? So let me just make a word. So, you know, the homology of function spaces is not such an easy thing to understand. Okay? And you know, Poincaré defined the homology of spaces. The homology of function spaces, the first non-trivial work was probably the work of Morse, where he studied the maps from the circle into the sphere, and then, you know, maybe Bott went a lot further, and he looked at the loops into compact Lie groups and into homogeneous spaces. And in all of those cases, there were beautiful, beautiful pictures. And what was really great is having beautiful pictures means that, you know, you could now, I mean, I explained how last time, you know, Morse theory really is a theory about persistent homology, but that the infinite length bars are topological, and the other bars, one should think of as carrying geometric information, which just the earlier generations weren't interested in. Okay? So, so when the original techniques of like Morse and Bott apply, you always get something that's like this non-positively curved picture. Some function or other is perfect, which means that you get a critical point, and the critical point builds homology, and being perfect means that whatever is born never dies. It's some kind of utopia. Okay? But, the really big advance in understanding homology of function spaces came in Serre's thesis, where he introduced spectral sequences, which are a big, elaborate, to some set of heathens, I know to the initiated it's like bread and butter and it's really trivial and obvious, and but anyway, it looks like it's a certain kind of elaborate algebraic apparatus, at the end of which you don't directly see the homology. You get access to it by associated gradients of some filtration, things like that. It's sort of a much more mysterious method. Now, it turns out that it's powerful enough that tells you that if the target Y, it tells you sort of amazing things, right? Like which seem. It says that you could, in particular, try to understand. How do you prove something like this? Maybe that's something that I should talk about, right? Where does this come from? Right? So what Serre does is it gives you an algebraic apparatus, and it says that therefore you could try to understand this object. And then after the fact, right? Everything is an algebra, right? And in algebra, you don't have to pay every time you use an equivalence relation. Right? It's completely free. It's like, buffet, right? Here, the real problem is, right, that I'm being asked to pay every time I use one of the defining relations in the fundamental group, right? So if every time I have to use a relation, I have to, pay the guy who has a patent on the relation, when I have a very difficult word problem, I got to pay a lot, okay? Right? So, algebra is complete, algebra by its nature, looks very, is kind of insensitive to these things. But what you could after the fact is, look, if I have an invariant around that detects this, so we talked about the case of mapping the n sphere to itself, right, where the invariant is the degree. And then we observed that if the Lipschitz constant was less than L, from one definition, if you count the number of inverse image points, that number might grow really, really very fast. But if you're careful and you do the average number, and you bring in differential forms, you discover that, the degree is at most L to the n. Okay, and then that gives you a polynomial bound. Okay, so after I tell you that, the rest, I told you on one foot why the theorem's true. Okay, and then the rest, you have to go ahead and do some algebra. Okay, and you get out this theorem, but this kind of theorem, but what's the nature of that theorem? The nature of that theorem doesn't tell you. I look at these, I have like these L to the n different components from the point of view of infinity, by going all the way up. But I don't know how high I had to go in order to produce the homotopy. So I don't have, right, this thing here tells me nothing about the long finite persistent intervals. Okay, now the long finite persistent intervals, for some problems they're the enemy, and for other problems they're your friend. Okay? For the problem of closed geodesics, they were your friends, right? Every time you got one of those intervals, down at the bottom, there was a closed geodesic waiting for you, and who wouldn't be happy being presented with a closed geodesic? Okay, right? So that's sort of a great thing, right? But then other problems, so let me, so I want to talk about, these kind of things, where persistent homology is the enemy, what kind of things might be true about it, and also why it's not enough. Okay, so let's think about the case of Sn to Sn. Okay, and I have F, and F is L Lipschitz. Okay, so what does such a function look like? Okay, so this is my picture of Sn. It's the okay, it's this.
No, but he switched.
Oh, okay. Okay. No. Spectral sequences are what So from the point of view of spectral sequences is that they just tell you about the infinite length bars. They only tell you about the topologically invariant things. Okay? And for some of our purposes, right, I mean, trying to understand quantitatively, you know, all of the things that we know just that something exists, right? So I'll maybe get back to the theorem I mentioned at the very beginning of the series, right, about where, you know, with the theorem of Gromov, Lawson, and Stoltz, where some kinds of metrics exist, and you want to know the properties of those metrics. So then you have to go through, you know, you need more precise information than just what happens for infinite length, right? You know.
Spectral sequence also gives you the information on each step, so it's also gives you some information on the middle step.
I mean,
Because each list of the spectral sequence is functorial in some sense, and it gives you some
yeah, no, but yeah, so, yeah, I can't answer that question very quickly, all right? I could answer it slowly, but not quickly, all right? You know, yeah, so let me say to you like this. Okay, if I want to map, you know, there's a very simple way to understand this, and I was about to explain it the simple way, which was the way Brouwer originally understood the theorem. But if I wanted to understand this the complicated way, a la Serre, right, I would say, how do I understand maps from Sn to Sn? I think of these as being a one-parameter family of maps from the various slices, you know, right? And I think about this as a map from Sn into the loops. Yeah, so that isn't the right picture, but there is a right picture. Okay, right? I mean, I should have drawn them like that. Right, that for every point on the equator, I have a loop. Okay? And now, the loops of Sn, we decided that that's not such a bad thing to look at. Okay, and you know, we built some combinatorial model, and when we put in the Lipschitz constant, we understand how the combinatorial model is changing. So you could imagine beginning to do such a thing. Okay.
There's a question from the Zoom
Yeah.
about the converse of the last.
In a slightly more precise form, there's a converse. Okay. In this form, there isn't quite a. I'd have to think a little bit, okay? There's a slightly stronger form of this theorem that has a converse, okay? And
Thank you. I'm talking about this already.
Yeah.
Could you please remind us, infinite length means that
All bars are infinite.
or just some bars are infinite?
so there are some bars that are infinite length, and all the ones that aren't, well, by definition, they're finite length, but the statement is that not only are they finite, there is some number that bounds all of them, okay? Okay? Which is exactly what doesn't happen, right? I mean, when you know, say in this word problem kind of example, right, where there are infinitely many intervals of larger and larger length, because if it was a bound on them, that would, you know, then you'd really be able to get very specific algorithm of specific side. Okay, you know, yeah, yeah. I mean, somehow what happens is, you know, you take simple spaces like Sn, which they start off being beautiful and geometric, but the very next step is that you replace them by a function space. And doing that, you have to then do something to make them into more geometric objects. And as far as we know, there's no way to do that without losing an exponential amount of information. So if you have to go ahead and do this process k times, you typically can get yourself a tower of exponentials. Okay? So it isn't the case that there's no information that comes out of the algebra, but as far as we could see, the information you get is much, much weaker than is in fact true. Okay? And it's sort of not a matter of, you know, that it's not that there's some algebraic principle that we're missing. It's that the kind of models of the space is naturally have some kind of exponential amount of distortion from the truth. Okay? So, I mean, so everything gets done by an induction. Each step in the induction, you've lost more than you want to. So at the end of the induction, you're just way, way, way off. But the good news is, so the theorem of Serre formally implies that the persistent amount that when y is simply connected, all the bars of finite length, there is some computable function of the bottom of the bar that will bound where the top of the bar is. Okay, that's what's sort of a formal consequence. But a more careful version of doing this would, I believe, give you a tower of exponentials. Okay, and at least for pH0, there's a theorem of Manin that tells you that the length of the bars are at most polynomial. Okay, and there's a conjecture that's probably due to Gromov, which would say that it should be linear. Okay, I mean, okay, so. But I feel I'm not explaining anything when I say all of this. Okay, so what I just want to think is, so let me just think about concretely just one very simple case. And, right, so I'm going to go from the sphere to the sphere. And the map that I have in mind, all of these things here will go to a base point. It's just going to be constant out of a bunch of balls. Okay, and, in these balls here, they're going to be of length like, their Lipschitz constant is, I don't know what to say. Yeah, they should be of size like 1 over L, okay, where 1 is some number like pi. Okay, so the center goes to the North Pole. Okay, they then stretch it over the whole sphere. Okay, and then on the boundary they go to the South Pole. Okay, and, a little bit of geometry says that if I have any L Lipschitz map, I could homotop it through some constant depending on geometry. I mean, I don't say 5L to something that is normalized in this way. Okay? Okay, so that's a picture which you should take on trust. Okay, that it's just true and not very hard. Okay, it's sort of the level of depth of the proof of the homotopy extension principle. I mean, it's, sort of elementary topology tells you that this is a model for what the functions look like. Okay, so that's all good. And then the Brouwer degree is just deciding on each of these things. Was it orientation preserving or orientation reversing, right? So there's sort of two kinds of things. There's a plus and there are minus balls. Okay, when I map to it, and the Brouwer degree. Okay, and now among these things, by the way, it's obvious that the number of these balls, if I'm going to be normalizing this way, is at most L to the n. So this gives you, again, a geometric version, not using the differential forms, about once you know Brouwer's theorem, about, why there are at most L to the n homotopy classes. Okay? But this is now the picture of the maps. Okay? Now, if I have, so now I'm going to draw the picture on its side. And if here I have a plus, and here I have a minus, there's a maneuver I could make, which is I could take an interval that connects the plus to the minus, okay? And I could extend over here, but now it's the same map on both sides, right? Just extend the map, and here I, use a constant. And that defined, the beginning of an extension. If I don't do anything else anywhere else, then there's sort of an obvious extension. Right? I mean, just, okay.
SN cross I?
Yeah, this is a picture of SN cross I. And basically, the way you prove the theorem now is that if two things, suppose that something has degree 0, so that means that the pluses and minuses, the pluses and minuses, can be paired with each other. So what do? I take a plus and a minus, and I draw an interval like this, and I do a cancellation like that, and everything else I just, don't do anything with at all. And then I'm at a lower level, okay, and now I have I have pluses and minuses, and then I do another cancellation. Okay? And and that's the proof of Brouwer theorem. Okay, right? So, first I take the map, I normalize it this way, and then when something's normalized, I realize that all that there is counting pluses, minuses. And what do I have to do? I just have to do this kind of cancellation. Now, of course, you might have bad luck. If you draw this thing and, you're underneath a place where there was a plus, and my plus wants me to drill directly down, but now I want to have this tube that goes between it and intersects, then I get a conflict and and I go, it's very bad news, right? So, now somebody might tell me, oh, what you should really do is do the plus and the minus that are nearest to each other. Do that cancellation so then I don't run into this problem. Okay? Right? But now if I do this, and let's just think about this map, okay? This map really, if I worry about the Lipschitz constant in this direction, right? Doing this maneuver costs whatever it costs. And now it looks like I have a homotopy of length L to the n, right? Because they're going to be around L to the n over two pairs of guys that are canceling. Everyone waits their time patiently, right? And then they get to be canceled. And then so the homotopy that comes out, if you're interested in the Lipschitz constant of the homotopy, okay, so if you're just studying persistent homology, then you're not asking. You're just asking, is there a path where the Lipschitz constant never goes up very much? And we understand that problem. Okay, right? That problem, we do one at a time. We do the cancellations, and we see the answer is yes. I could do the homotopy without increasing the Lipschitz constant more than a little multiplicative amount. Okay, that's really tacit in the geometric proof of Brouwer's degree theory. Okay? But if I want to do something better, and I'd like to know, given f and g, that map Sn to Sn, is there, and both L Lipschitz and the degree of f equals the degree of g, right? So then I know there is a homotopy, but now I want to know, is there a CL Lipschitz homotopy? Okay, right? That's the question that I'd like to, right? That's the question that maybe I want to study. I decide that, why be quantitative just on the size of the individual slices? I should be quantitative in the notion of homotopy. Okay, then you have an interesting question about, is it really an equivalence relation? Anyway, but I'm not going to worry. And yeah, so you want to say, does there exist a C that, will depend on n, such that whenever f and g are L Lipschitz and homotopic, can you improve it to a CL Lipschitz thing?
Since you just proved
And
last time that it depends on the homotopy groups of the spheres, the information about the homotopy groups of the spheres.
Let me return to that in a second, but I want to point out that this theorem includes that the answer for when you have finite homotopy groups is always yes. Okay? So the problem that we see in the first non-trivial case of pi n of Sn turns out to be more non-trivial, naively, than what happens in the general case. So let me first talk about why does finiteness help? Okay, so what causes us to struggle? Okay, if I wasn't interested in looking too carefully at the thing, right? I mean, like Brouwer was, right? Brouwer didn't particularly care about measuring Lipschitz constants, right? You could take any pairing, right? I mean, I could connect this one to that one to that one. If my sphere is more than two-dimensional, I could, or any pairing. I mean, I could always find some bunch of curves. Okay? And then I take little neighborhoods of those curves that are disjoint from each other, and then I push them all in and, define the maps along those, and that would work. And then I just have to see how skinny were the tubes I made, in the course of doing those. So, right, in order to improve this, I might get replaced by a different question, which is how skinny, if I want to put in all the spaghetti at once, how skinny, how close does the spaghetti have to get to each other? Okay, so that is a question about, so that's some kind of isoperimetric question. on Sn, right? So I have a whole bunch of points, and each point I choose to put a label of a plus and a minus, and then I want to connect them by curves. And I'm interested in how close do those curves get to each other, okay? And the answer turns out to be yes, that there is a C, and this C depends on is really a fact about the isometric geometry of this n-sphere. So in the thing that you mentioned, I was asking this where something was supposed to be independent of the domain, except as far as the dimension was concerned. So now you'll be seeing that isoparametric constants enter. So once you see that there's some amount of geometry of the domain enters into the answer, that turns out to be, why you had that aspect of the previous theorem. Okay, that when you have an infinite homotopy group, then actually the geometry of the domain enters. Okay, suppose that instead of being the sphere here, I have some target, I don't really know, but the way it would be ramified would be that at each of these things, I get an element in a finite set. Okay, right? And then my pairings are, of course, not, there are various things. This finite set is going to be an element of a homotopy group, of course. Right? It's a finite set. And now I'm interested in doing things like pairing things locally, right? Okay, I don't have any, right? I mean, the point is that if everything is in a finite set and I'm willing to introduce some kind of canceling pairs, okay, then it's not so hard to go ahead and build all your spaghetti to be made out of very, very small strands, right? For example, if it was all in the group Z mod 2, then I'd have an even number of these, and then if I have some number of things, I would just connect each guy to the closest neighbor, right? So for Z2. For Z3, it's more complicated, right? Exactly. But the basic point is that if I have a finite group, then all of the spaghetti I need is local spaghetti. And local spaghetti, could be they could be fettuccine, right? I mean, they don't have to get very skinny, because whatever happened locally is the same thing that's happening locally. Okay, so that's sort of why when the target has finite homotopy groups, it's sort of, you're never forced to, to have long strands of spaghetti. Okay, but of course, there is an extreme case, right, where I put all of the pluses in the northern hemisphere and all of the minuses in the southern hemisphere. Right? So there's around L to the n over 2 positive points and L to the n over 2 negative points. And of course, every strand of spaghetti will have no choice but to go through the equator. Okay? So, you all of a sudden see that the equator acts as a bottleneck. Right? And, and that tells you that they have to be skinny at scale 1 over L, or something like that, right? I mean, they're going to be, this has air, right, at scale, rescale everything so that this 1 over L to the n looks like a 1, okay? So then at that scale, this has volume L to the n, and this thing here has surface area L to the n minus 1. So you typically are going to have around L strands going through something of unit volume. So that tells you that they have to be getting closer. But of course, if this was really the picture, in terms of building the map from the ball, I would do the strands like this. Okay? So this is the fact that if I'm looking at an L-Lipschitz map from X cross an interval, the width of the interval gets multiplied by L, so that's okay. Okay? All right? The number of points, right, and the number of points that goes up grows with the Lipschitz constant, right?
Yeah. Okay, so that's going up linearly with the Lipschitz constant.
Yeah.
But the lengths of the curves aren't allowed to go up? It's also bounded by Lipschitz constant? Does that mean the curve could get...
No matter how long the curve is, okay? So if you're, yes, the curve that you're going to have, it's never going to be longer than the diameter in practice. Of this space. I mean, why? Well, for the two-sphere, the way I describe it. Okay, so there are a few things that I oversimplified because I'm a poor artist. one of the things is that I imagine that these curves were really taking place in the sphere, but ultimately when you think about them, we were really pushing them in one dimension higher. Okay, so so there's sort of a little bit more room for manipulation than otherwise. Okay, now the next thing is that, and sometimes it's useful to always be thinking at a constant scale, so I'd like everything to be 1 Lipschitz, so then I might rescale the space so that everything so that's what it means to be working at the scale of 1 over L or something like that. You then, but I realize that it makes some of the discussion a little complicated. Okay, but what I want to emphasize is that, what the constant is that you would need for improving this is if I replace this sphere and I gave this sphere a different geometry, and I made it look more like an ellipsoid or something like that, then this middle equator would become more and more of a bottleneck, and that would force the multiplicative constant that you would need to go up.
Why do you think that this position of points is optimal?
So that's a non-trivial isoparametric theorem that you have to prove. Okay, so there is something or other that you have to prove, right? That what I described is in fact the worst possible scenario. That when you want to go ahead and, right, if you're interested in canceling pluses and minuses and you put them over the sphere, then the worst thing you could do is have all the pluses hanging out together and all the minuses hanging out together and try to do that, right? And so it's intuitively believable, but it is non-trivial. And it took me, well over a year to find the trivial proof, okay? But yeah, it's something that's obvious and in retrospect isn't hard, but it's hard to find the non-hard reason. So it's in my paper with Fedya and Dominic Dotterer and Greg Chambers and Jams a number of years back. Okay, but basically the phenomena that occur in this example, are ultimately they explain to you why when a homotopy group is infinite, some kind of implicit constant has to grow. Right? Why the geometry of the domain is relevant. On the other hand, these kind of considerations about cancellation, that it's exactly the explanation for why this theorem is true. Okay? But you have to put it on steroids. It's a simple picture, but you have to just check that the picture actually applies no matter what the space is. Okay, so that's therefore you do the proofs in algebraic topology. Okay. So anyway, so I could have been viewing this as a geometrical problem, right? So I could think about this collection of points with pluses and minuses. Let me think about that as being an oriented zero manifold in the sphere. Okay? And we did cobordism theory. Right? The cobordism theory of zero-dimensional manifolds in a sphere is all that there is the number of pluses minus the number of minuses, and the original proof of that was just you put in uncontrolled spaghetti. Okay? Now, an interpretation of our theorem is that, if I have a bound on the geometry of my zero manifold, okay, then I could get some bound on the geometry of the null cobordism. Okay? Okay. However, there was something non-trivial, right? The isoparametric, if I really wanted it to be embedded in the manifold, right? If I want to bound the geometry of the null cobordism, right? So I'm trying to understand what would that be? That might be something like the sum of the total length of all the spaghetti, right? That required some additional arguments. Okay? So I think I only have 10 minutes left, so I just want to return to the theorem that I said as motivation for this project. Okay? And then just point out where the aspects of it, which pieces of what I explained address which aspects of the theorem. Okay? So the theorem went something like this. So since this is the new thing, I'll be careful to give some names, which is Manin, Zhizheng, Xie, and Guoliang Yu. And it says this, it says let M be a simply connected, okay, I'm going to spin manifold, okay, where the curvature of M is less than or equal to 1, and the injectivity radius of M is equal to or greater than 1, right? So this is saying that locally there's not much topology, right? Balls will be balls at that scale, and that they look like the standard ball, you know, by a diffeomorphism whose second derivative is bounded or, you know, uniformly, right? I mean, it's really, really very standardized, and that the volume of M is, let's call it V. And I'm going to phrase it like this. Suppose M has a metric of positive scalar curvature. Okay, I'm not going to, again, tell you what that means. It had to do with volumes of small balls, of infinitesimal sized balls. Okay, then, oh, I even have it. Then, in general, the inf over families G sub t, such that G0 is G and G1 is positive scalar curvature, and all curvatures of the G sub t's are less than or equal to 1, and all the injectivity radiuses are at least 1, right? You know, you're looking at this family of metrics, okay? And then you're going to look at the soup of the volume of G sub t. Okay, so G sub 1 is going to be your solution to this problem. And you ask, in the course of discovering the solution, if you were to deform to this, so whenever there is a positive scalar curvature metric, there is such a family. I explained that. Okay, but now you want to find this the statement is that in general, this thing is greater than any computable function of V. Okay, and what this precisely means is if you give me a computable function like 2 to the 2 to the 2 to the V, then for sufficiently large V, I could find on this manifold M a metric with these properties such that any path to the solution has this inf soup bigger than that function. Okay? That's what it means, sort of, by what I mean is in general. I mean, it can't be for every metric, because G0 could have been itself the metric of positive scalar curvature. And for that, this inf soup will be just V itself. Okay? So that's sort of part one of the theorem. Okay? And you already know that the secret here, so I mean, of course, I'm looking at the persistent homology of V viewed as a function on some space of metrics. Okay, that part involves no secrets. Okay, and somewhere or other, there has to be an undecidable problem embedded within this. And the undecidable problem is this. I take a hypersurface inside of Sn plus 1, and it's given to me in some nice way, and I want to know, is it the n sphere or not? Okay, if it is, and I take such a metric and I just take the connected sum of that hypersurface with M. Now the question about whether I get M itself back or not turns out to be undecidable. Okay, and now that has a nice reasonable metric on it, et cetera, it's all nice and simple, and somehow doing that, you get a new manifold M that doesn't know it's simply connected. It's a manifold that under some conditions happen, you know. But a lot of the times it ends up that it is the manifold M, because otherwise it would be very easy to decide the problem, just so it's answer no, the hypersurface isn't. Right, so a lot of the times the hypersurface really was there. The hypersurface thinks it has some non-trivial fundamental group. Once it has a non-trivial fundamental group, then it doesn't satisfy the hypotheses of Gromov and Lawson, and you can begin trying to use that hypothetical non-trivial fundamental group to get obstructions to the manifold having positive scalar curvature. So the situation is you look at invariants that involve the group homology of the fundamental group if the fundamental group happens to be non-trivial. Okay, something like that. It's, you know, I mean, it's sort of strange, and it becomes really strange when you try to look at the quantitative aspects, but nevertheless, that's what's behind this. So it's really similar to what we said about the word problem. And then in the other direction, the statement is that inf soup of V of G prime, such that G prime has positive scalar curvature, is O of exp of V to the 1 plus epsilon. Okay? That there always is some metric on M that has positive scalar curvature, where the volume isn't too big. And again, I have no reason to believe that the truth here isn't linear in V. Okay? And the way this ultimately gets proved is once you know the first one and you know that logic is either your friend or your enemy, no matter which way you want to think about it. For this one, the point is you start off with such a manifold and you realize you're not going to deform the metric to be a positive scalar curvature one. Instead, what you try to do is come up with constructions which, if M happened to be simply connected, the new manifold you build would be M. If M happens to be non-simply connected, and I don't know how you're going to decide this, right? Then, all bets are off. So really what you associate is, in proving the theorem, you associate to M a doppelganger, M prime, where you produce a metric of positive scalar curvature, where you've controlled it to be somehow geometrically simpler, okay? And that's where you go ahead and do the work, okay? And now in the course of the proof of that, there are sort of two parts of it. This V to the 1 plus epsilon is basic. The V was best you could hope for. 1 plus epsilon has to do with the mimicking of geometry and topology. Okay, when you do cobordism theory, I said you take a manifold and we imagine it's in the sphere. So you have to embed the manifold in the sphere. When you embed a manifold in the sphere, you always introduce distortion. So somehow when you do all the optimizations, you still can't get a linear relationship. So that given that every time you take abstract manifolds and relate them to concrete manifolds, that's ultimately, a version of the source of the 1 plus epsilon. And then this exponential part is something that we really don't understand. It's somehow related to the proof of the Poincare conjecture in higher dimensions. But happily, this theorem isn't as deep as the Poincare conjecture. The Poincare conjecture should need a tower of exponentials because something or other is inductive. But here you only use one step of it. So each of these pieces is unsatisfactory for some reason or other, but I have no idea how to remove either of these. I could imagine getting it down to exponential. Well, anyway, I better stop for now. Anyway, so, but this is really related to this kind of thing that I was explaining today about linearizing homotopies. Okay, that somewhere or other you want to take your manifold and you want to cobord it to something and you want to bound the geometry of the cobordism, and that cobordism has size V to the 1 plus epsilon. And then the thing that you end up being cobordant to isn't your manifold itself, and building that new thing, that doppelganger, that had an exponential cost. Okay, and so that was why the talks were related to their motivation. Okay, so that's it.
Any questions?
I
Yeah.
understand correctly that when you are talking about deciding whether two manifolds are the same, you're basically passing to the PL category, using the fact that there's a difference between the topological and PL category.
So depending on my mood, I could answer yes or no to that question. Okay, so there's, the PL category is more naturally a category, of nice finite simplicial objects, and you feel that they're, you feel much more comfortable, talking about, decision process because everything is nice and discrete. Okay, so you have to go ahead and decide, how are you going to put in, indiscrete, non-discrete things, but if thanks to Nash, Tognoli, every smooth manifold I could view as being the locus of solutions, of a whole bunch of polynomials, and I could encode them, in perfectly good, in some perfectly good way, and I could specify coefficients, and put them, insist that they were algebraic. I mean, there are ways of making everything, you could talk in the smooth category, perfectly well about decision processes, and there are a couple of things, but the real trouble is, how you don't really ever want to talk about the sphere of radius r, where r is a number whose nth digit is 1 if and only if the nth Turing machine converges, or something like that, right? You don't want to put in undecidable real numbers when you put in an encoding of arbitrary manifolds. So be careful not to do that.
You're joking, the same. Do you mean the morphic equivalent?
All of those problems, so except for dimension 4, where all bets are off, the question of deciding whether M is homotopy equivalent to the n sphere, or whether it's homeomorphic to the n sphere, or homeomorphic to or diffeomorphic to the n sphere, all of those problems, are the same level of depth. Okay, homotopy equivalent is equivalent to homeomorphic, which is equivalent to PL homeomorphic. Okay, and the question of smooth structures, okay, there's a nice paper of Corvair and Milner that calculates the things, and it tells you invariance, so you have to study how do you measure those invariants. Okay, and then there becomes interesting non-trivial questions. They have some invariant, how do you estimate it in terms of the geometry of a manifold or things like that. But in terms of the question of decidability or not, they're all, it's the same problem, because Corvair and Milner is an effective solution. In principle, in dimension 4, it might be that we can't decide if a 4 manifold is, we don't know whether we can decide whether a 4 manifold is homeomorphic to the 4 sphere. Okay, and that's, in terms of the word problem, it's related to the question about if you have a group with an equal number of generators, and the question of whether a group is trivial or not, that we know is undecidable. But in dimension 4, what becomes more relevant is if you have a group which has an equal number of generators and relations. And we don't know any way of making undecidable word problem, undecidable triviality problems with that kind of thing. So it's conceivable that homeomorphism is decidable. It's conceivable it's undecidable. Diffeomorphism is way up. The algorithmic, not only don't we know the answers to the Platonic questions, we also don't know the algorithmic, answers. I mean, of course, if it's in a world where everything is true, then the answers to everything is just going to be yes by some trivial, for some trivial reason. But yeah, all of these things, they're easiest to say in one way, and there's a comment that I should make about, given that the paper on smooth cobordism was written about close to 10 years ago, and PL cobordism is a preprint that just came last month, that in fact PL is much harder than smooth, even though algorithmically it looks simpler. And that has a very simple geometric reason. So that I should explain. It comes in a couple of layers. Firstly, for a smooth manifold, what ends up entering is you look at the points of the manifolds, and you take the tangents, you look at their normal directions, and you map that to a Grassmannian. There's a specific manifold, there's a specific target you go to. The manifold gets a map to the Grassmannian. A neighborhood of the manifold in Euclidean space gets mapped into the tautological bundle on the Grassmannian. And then you map the whole sphere into the one-point compactification of this. And that's a nice compact polyhedron. Okay, and the geometry of the manifold you somehow want to embed in studying the Lipschitz constant of that map. Okay, and so there's a problem about making the Lipschitz constant small, and then there's a problem about understanding what the Lipschitz constant of the null homotopy is. Okay, but the good news about all that is that the target was a nice finite complex. When you're doing PL, there's no such thing as a PL Grassmannian that's a real live space. I mean, the kind of spaces that algebraic topologists use in studying these problems are produced by what's like the Brown representation theorem. Some functor is representable. You don't know what the hell you're talking about. Excuse me. I mean, you don't know at all what you're talking about, right? I mean, it's sort of a fantasy space. You say that there exists a space with these properties. So what do you mean by a Lipschitz function into a space whose points you don't know? Okay, it sort of feels meaningless. So it's a fundamental problem. One has the feeling that understanding these kind of analytic questions about the maps in algebraic topology that arise when you translate geometric topology into algebraic topology, that's the core of the issue. But then a fundamental problem is that most of the time you don't know what you mean by a Lipschitz map. Okay, so we developed some technology for dealing with that problem. And then a very interesting feature comes up when you do that. Which is, what do you mean by a PL manifold? Okay, so I could imagine a simplicial complex that happens to be a PL manifold. Okay, and that would mean that I'm, that if I look at a vertex and I ask how many neighbors it has, I'm not insisting on that. I'm just insisting that the link of the vertex happens to be a sphere. But you see, happens to be a sphere is a thing that's hard to check. Right? That's the thing that we just said was undecidable that was behind this, growth over here. So you really don't want to allow arbitrary local geometries. Okay? You don't want to have to rely on an oracle to decide whether or not you even have a problem, right? Someone gives me this thing and it says, I want to know if this PL manifold bounds, and I say, well, I don't even know if it's a PL manifold, right? I mean, that seems like that would be sort of disastrous. So if you go ahead and say, I'm going to insist on a bound on the geometry, okay, you have to put that in at first, right? That you bound the number of neighbors in advance. And then the theorem is that you get if you have V simplices, then the null cobordism, if it exists, is of size V to the 1 plus epsilon. That ends up being the thing. But there's an implicit constant, and the implicit constant, right, there's a constant at the beginning of the thing, which is how many neighbors do you allow your thing to have, and then there's an implicit constant that depends on what that depends on, and that thing probably grows like a non-computable function. And all of that is somehow reflected by the fact that in the PL world, one's really dealing with a fantasy space, right? It's a space that doesn't, that a normal person wouldn't allow into into their home, but the algebraic topologist said it exists, so you deal with it. Okay, but by the way, I mean, all the prejudices that I assert today are prejudices just for the moment. 10 minutes from now, I'll go drinking with that space. I mean, we're really friends, but it's just very hard to deal with sometimes. Okay. Yeah.
So maybe we should thank Shmuel for a great series. So you'll be in Israel.
Yeah. I mean, right. The next 3 weeks I'll be in Weitzman, so not so far. Then Jerusalem. And